Hi everyone, today we will discuss problems based on concept of electrostats. So you can see the first example. So here we have a pith ball, a free pith ball of mass 5 gram carries a positive charge of 100 by 3 nanocoulomb. What must be the nature and magnitude of the charge that should be given to a second pith ball fixed 5 centimeter vertically below the former pith ball, so that the upper pith ball is stationary. So here the question is, there is a pith ball. So suppose we have this ball, mass of this it is given, that is 5 gram. Okay. Now it carries a positive charge 100 by 3 nanocoulomb. So Q is also given, that is charge Q is equal to 100 by 3. Okay. Now the charge carried by this, it is positive in nature. Now the question is, what must be the nature and magnitude of the charge that should be given to a second pith ball? Second pith ball, okay, fixed 5 centimeter vertically below this. So 5 centimeter vertically below this. I am taking this distance center to center, from this center to this center. Okay, 5 centimeter vertically below the former. If nothing is mentioned as far as the separation between the 2 points or distance between the 2 points are concerned, or 2 objects, we generally take from center to center. Fix 5 centimeter vertically below the former pith ball, so that the upper pith ball remains stationary. So what should be the charge given to this ball, which is 5 centimeter vertically below this? Mass of this it is also given, charge on this it is also given, the nature of the charge it is also known, that is positive in nature. Now what should be the charge given to this ball so that it remains stationary? Now why should it move? It will move just because of force due to gravity. So it has this weight acting in the downward direction. If you consider this mass m is equal to 5 gram, so it is mg of this, it is acting down. Because of this, it will have the tendency to have free fall motion. It will try to move down. Now nature of the charge, it is positive. So if there is some force acting on this which can oppose this or which can balance this weight of this or the force due to gravity, it means this will remain stationary, because this is the only force or this is the only pull which can bring it down. So if that force is balanced, it means in that case this will remain stationary. Now what force can balance this, or which force can balance this? This is having positive charge. This force already acting on it, it is in the downward direction. If we have a force acting on this in the upward direction, and if this force can balance this, then this object, in that case the summation of force acting on this ball, it will become 0, so that it will maintain its equilibrium position or the static position, and it will remain at rest. Now from where should we get this force? This force we will get if a similar charge is provided to this ball. So if similar charge is provided, as far as the nature of the charge is concerned, if the similar nature of charge it is provided to this, then there will be force of repulsion between these two. So this will try to repel it in the upward direction. So that force of repulsion in magnitude, if it can balance this weight mg, in that case this will remain stationary. It means here the charge nature is positive. Force of repulsion, it will be there only when this ball will also carry the similar nature of charge, that is positive. So this is clear from this direction, in what direction this force should act. So from there we got this nature of the charge. Now to calculate the magnitude of the charge given to this ball, this mg should be balanced by force of repulsion between these two. So if force of repulsion between these two, let us assume charge here it is q1, charge given to this it is suppose q2 in general, then that force here, the force of repulsion, it should be k q1 q2 upon r square, where r is the separation or distance between these two. So this is the general relation. Now if this F balances this mg, then this will remain at rest or it will maintain its stationary position. So that's what we have done here. Q1 this is already given. Q2 it is taken as Q. 1 upon 4 pi epsilon naught. This clear. because the medium here it is air. So it is 1 upon 4 pi epsilon naught r square. That is 5 centimeter. Change it to meter. So 5 into 10 power minus 2. So r square. Simplifying this, we will be able to calculate this Q, because this is the only unknown, because this F should be equal to how much? The weight of this block, so that this remains at rest. So weight of the block, that is mg, simplify this, that is 5 gram, 5 into g into 10 to the power minus 9, this is your conversion factor there, and simplify, you will get charge Q is equal to 408 nano coulomb. So if this much of charge is provided on this ball, which should be positive in nature, in that case this object or this ball will experience a force of repulsion which will be able to balance this weight mg, and the system will remain, or this object will remain at rest. Now see this question here, 2 drops of water, okay, each with a charge of 3 into 10 to the power minus 9 coulomb. Let us say here it is Q and here also it is Q. 3 into 10 power minus 9 coulomb, and having a surface potential of 500 volt. Any potential across this or potential across this, the surface potential, okay. Having a surface potential of 500 volt, form a single drop, and these two charges are combined so that they form a single drop. Then calculate the surface potential of the new drop so formed. So now these two drops have been combined, or they have been merged to form a single drop. So what will be the potential of that drop? That we need to calculate. So Q charge on each sphere, it is given as 3 into 10 to the power minus 9 coulomb. Charge, it is a conserved quantity. Total charge always remain conserved. In the previous lectures we have discussed, charge remains conserved, mass remains conserved, total energy is always conserved. These are conserved without any restriction or condition. But momentum also remains conserved, but that remains conserved only if summation of all external force acting on the system, if it is 0. So in that case there is a restriction or condition as far as momentum conservation is concerned. But for all other 3 parameters like mass, total energy, as well as the charge, we don't have any condition. They always remain conserved or constant. So here, when we merge these two, it means the total charge on the single drop, that will be what? The combination of these two, that is Q plus Q means twice of Q. Now a radius of each of these smaller radius, let us say R, and after they are merged, radius of the bigger, let us say it is capital R. Okay. And the radius of the bigger drop, suppose it is capital R. Now the surface potential of a smaller drop, it is given as 500 volt. Total volume of the two drops, why we are calculating the volume? Because the mass will remain conserved. Even if they merge, the mass will remain conserved as well as the charge will remain conserved. So from that we try to get the unknown quantity. So the total volume of the drops, spherical surface volume is 4 by 3 pi r cube. 2 of these spherical, so twice of this. So this is the total volume. Volume of the bigger drop, it will be 4 by 3 pi r capital Q. Now see this here, total volume. Now here we don't have to equate the total volume. We should equate the mass, because mass always remain conserved. But before they are merged and after they are merged, they are of the same density. So volume into density, that becomes what? Mass. So that density terms, it will be eliminated. So that's why we are not considering this row here, and we are only considering the volume. If the material would have been of the different density, then we should not have considered only the volume, we should have considered the masses, because the mass remains conserved. So in that case, rho 1 as well as rho 2, then we will equate m1 and m2, and the unknown quantities will be calculated based on those concepts. Here density remains same before they are merged or after they are merged. So here when we consider the total volume, so multiplied by this density rho, so that becomes the total mass. Similarly, volume of the bigger drop, it is 4 by 3 pi r cube into rho. Sorry, volume of the bigger drop 4 by 3 pi r cube, mass of the bigger drop, it becomes 4 by 3 pi r cube. Now from the concept of mass conservation, this will be equal to this, rho and rho it is eliminated, so that's why we have equated this. 4 by 3 pi r cube is equal to twice of 4 by 3 pi small r cube, and from there we get this relation between the radius. Capital R is equal to 2 to the power 1 by 3 small r. Now potential it is q upon r in general, and if you take that constant it is 1 upon 4 pi epsilon naught q upon this r. So for the smaller surfaces, potential it was how much? 1 upon 4 pi epsilon naught 1 upon this r, small r. So that means q upon r is equal to 4 pi epsilon naught capital V. That V is given. Is clear? Total charge on the bigger drop, it is twice of q. From the charge conservation, q plus q, total charge here it will be twice of q. Here over this it is twice of q. Now if we consider this, so surface potential of the bigger drop, it will be how much? Total charge upon radius of this. So total charge is how much? 2q. Radius we have calculated, that is capital R in terms of small r. So it is 2q upon capital R, obviously constant 1 upon 4 pi epsilon naught. So here we have this capital R is replaced by this. This already we have derived. Now simplify this and you are getting this 794 volt. Okay, so we have the surface potential over the smaller block. We need to calculate surface potential over the bigger block, or you can say bigger surface. The total charge q upon r with this constant 4 pi epsilon naught. Capital R we have calculated in terms of small r. Q upon small r it is known. From there we can calculate the value of small r, because q is known and v is also known. So that gives you value of small r. Once you get the value of small r, substitute here and you will be able to get the potential or the surface potential over the bigger surface. That you can see here again. See this q upon r. This q upon r is 4 pi epsilon naught v, and v it is also given. Q is also given. So from this we can calculate small r. Once you calculate small r, from this we can calculate bigger r, and from there we can calculate all this. So substituting or replacing these values, we can calculate it. So this gives you this. I hope this is clear. Now see this question. Here two identical charges capital Q each are at a distance of small r. So these charges A as well as B at a distance of small r. Charge value it is Q here, and here also it is Q from each other. A third charge small q is placed on the line joining the above two charges such that all the three charges are in equilibrium. Now a small charge q is placed somewhere between these two such that the system remains in equilibrium. It means none of the charges are moving. This charge, or this charge, they are all maintaining the equilibrium position. Equilibrium. What is the magnitude, sign and position of the charge small q? Means at what distance it should be located, this small q. What is the nature of that charge? And what is the magnitude? Nature means what is the sign of that charge and what is the magnitude of that charge. That we need to calculate. So when the system is in equilibrium, it means force of interaction, whether it is force of interaction between these two, it should be same as force of interaction between these two. That is, whether it is mutual force of attraction or mutual force of repulsion, that we don't know till we consider the nature of this charge. Whether it is mutual force of attraction or repulsion between these two or between these two, it should remain same, then only they will remain in equilibrium. Other is, when this and this also remains in equilibrium, it means force between these two, it should also be same as either force between these two or force between these two. So we will make use of these concepts to calculate all our unknown quantities. So here you can see just see this discussion. If the charge small q is placed outside the line AB, This is your line AB. This is within this AB, outside this side as well as this side. Okay. Now this statement says if the charge small q is placed outside the line AB, then forces due to charge at A and B on Q are in the same direction. Let us say you place this small charge Q this side. So it means this will apply force on this in this direction, as well as this will be apply force on this in this direction. So forces will be acting in the same direction. So there is no question of any equilibrium, because force will have to act in the opposite direction. Then only there is a chance that they will be able to balance each other. If they are acting in the same direction, then who will balance that force? Similarly, if you consider charge this side, okay, same situation will happen. This will try to repel this side, and this will charge as well as this. So again there will be force in the same direction. So again there is a chance that there will be no condition met as far as the equilibrium is concerned. So therefore the position of the charge Q must be somewhere between the line AB. It means it will be somewhere between this A and B. Then only there can be force of attraction. Suppose, depending on the nature of this charge small q, this will try to pull it this side and this will try to pull it this side, or this will try to repel it. So either this will try to pull it this side and this side. So in that case, there is a chance that these forces can balance each other, because there will be force of repulsion between these two charges, there will be force of attraction between these two charges. Though both the direction it will be opposite to each other, and when they are opposite to each other, summation of that force may be equal to 0. And when summation of that force is 0, then only we can think of equilibrium or static situation. So now let us, so one thing is clear, that small q, it should be placed somewhere between A and B. It should not be out of the line AB, neither this side nor this side, somewhere between that. So now we need to locate that, as well as we need to find the magnitude of that charge small q. So for the equilibrium of charge small q, here you have this small q. Force applied on a small q due to A, any force by this due on this, that will be equal to how much? 1 upon 4 pi epsilon naught q upon RA square. Distance between these two, it is taken as RA. So it is RA square. Similarly, force on charge q due to force on q due to charge at B, that will be q upon RB square, means this. Now, to be in equilibrium, these two forces should be what? Same. It means F of QA, it should be equal to F of QB, means force experienced by this charge due to this as well as due to this, it should balance each other. Then only this charge will remain at rest or in equilibrium. So FQA is equal to F of QB. Now, Q can be of the same sign or opposite sign of Q. So Q can be of the same sign or opposite sign of Q, means either Q can be of the same sign or Q can be of the opposite sign, because here suppose if this is positive and this is negative, so there will be force of attraction. So this will try to attract this side and this will also try to attract this side. So it means both the force, they will be opposite in nature, so they can balance each other if that is negative. Now if they are of the same sign, suppose this is positive and this is also positive, so here between these two there will be force of repulsion this side, and because of this there will be force of repulsion this side. So due to this it will be this side, due to this it is this side. So again these two forces can balance each other. So either it can be of the same nature, either they are positive all, or they can be negative all. So it can be opposite to this, it can be positive to this, so it hardly matters. Okay, now where should, so in that case RA is equal to how much? RB, because Q and Q it is same for both. You can see here Q and Q it is same, small q it is same, this is equal to this, so obviously this denominator and this denominator has to be same. So in that case we get RA is equal to RB. It means it should be kept at the mid position in equal distance, this and this. So RA it should be equal to RB. Okay, so I hope it is clear till now. So we have generalized what should be the nature of this and what should be the position of the charges and why. So that also we have considered. Now just consider how to calculate the magnitude of this. For the equilibrium of charge Q at A, now we are considering charge Q at A. Here we have this. We have this Q here, we have this Q here, this is suppose your A, this is B and small q somewhere here. This is your RA and this is RB. This total distance is R. Okay. Now if we want Q in equilibrium, because the system is in equilibrium, it means each and every charge is in equilibrium. So for the equilibrium of Q at A, for force on the charge Q at A by small q, that will be QQ upon RA square. Now we are considering force on this. Initially we were considering force on this. Due to this, this is in equilibrium, so we have equated. Now for the equilibrium of this, we are calculating force on this due to small q. So you have this relation. Okay. RA, we have taken R by 2 because we have already decided that it is in the mid of this. So RA or RB, it will be same, and that is R by 2 and R by 2. Similarly, force AB means force on charge Q at A by charge Q at B. Force on this due to this, because it is experiencing force due to two charges. One is this small q, another is this bigger q. If it is in equilibrium, so both the force again, it has to be balanced. So force on charge Q at A by charge Q at B. So that is equal to this, because Q square upon this entire distance square, so R square. F of AQ, it should be equal to F of AB. That minus sign only indicates that both will have to be in the two opposite direction. If it acts in this direction, then it should act in this direction on this charge. And if you have this Q at A, due to this, let us say it is this side, and due to this it is this side, then only this will be balancing each other, this force or this force. And that's why we have this minus sign. F of AQ, it should be equal to minus of F of AB. If you equate it using this relation, you will find small q is equal to minus of q by 4. Small q is equal to minus of q by 4. Now this minus sign indicates what? This is small q, it should be opposite to this capital Q. If this capital Q, if it is positive, then it should be negative. If capital Q is negative, it should be positive. This relation has not given us the exact nature of that Q. It has just given us a possibility that Q can be of the same sign or opposite. Either it can be of the same sign or it can be of the opposite sign. So both the options are there as far as discussion till here it was concerned. But what should be the exact nature of that? That we have to find, whether it is positive or whether it is negative. So that we got it from this relation. So now this gives you, now this relation gives us the magnitude of the charge, that is small q, it should be 1/4 of the capital Q, and using this concept that these two will be balancing each other provided they are opposite to each other. So that sign or that concept gives that this Q, it should be minus of q by 4. It means Q should be opposite to capital Q. The previous relation was either it can be, small q can be of the same sign of capital Q or it can be opposite. But out of those, which should be the exact nature. So from here we get that exact nature. So the same result is obtained when the condition for the charge B. So we have considered here, this was your A, this is B. We have considered a force on A due to this as well as this. Same logic you can apply considering force on this due to this or this, and we will get the similar relation or similar result. Either of that you can take, you can proceed, and you will get this. So the charge nature should be negative. Magnitude of the charge, it is 1/4 of the capital Q, and it is located in the mid of capital Q and capital Q. If both those charges Q and Q would have been different, then again the location, it would not have been the midpoint. It could have been either shifted left or it could be right. So now in this question you can see example 4, an infinite number of charges each equal to small q are placed along the x-axis at x equal to 1, x equal to 2, x equal to 4, x equal to 8 and so on. When suppose this is your x-axis, this is origin. Okay, now the charges each equal to q are placed along at x equal to 1, x equal to 2, x equal to 4, x equal to 8 and so on. So here we have this q, q, q and so on. This is given as 1, this is given as x equal to 2. So this is 2, this is 4 and this is 8. Because distances always it will be measured from origin. So 1, this is 2, this is 4 and this is 8 and so on. Okay. Now find the potential and electric field at the point x equal to 0. So we have to find the potential as well as the electric field at the origin. Due to this set of charges, due to all these set of charges, we have to find the potential and intensity at the point O. Now, so let us see this. Potential, it is how much? Q upon R. Potential V, it is equal to 1 upon 4 pi epsilon naught Q upon this R. And intensity due to, this is due to a point charge at a distance of R. This is potential. The intensity due to charge Q at a point at a distance of R, it will be 1 upon 4 pi epsilon naught Q upon R square. Okay, so these are the relations, because intensity is what? Force per unit charge, and force between the two charges is what? K Q1 Q2 upon R square. If you consider Q2 as 1, force between the two charges, and that is experienced by unit positive charge. So if you consider Q2 is equal to 1 and Q1 is equal to 1, Q1 is equal to Q, then it becomes Q upon 4 pi epsilon naught R square. So from there we get this intensity as well as this potential. V is equal to what? If you consider the relation between this E and V, all these things we have discussed in the previous lecture. So here E, it is equal to minus of this dV upon this dx. So from here dV upon this dx. So we get all these relations. F is equal to your Q1 Q2 upon R square. K Q1 Q2 upon R square. Intensity is force experienced by unit positive charge. So suppose Q2 is 1 and replace Q1 by Q in general. So this becomes KQ upon R square. So KQ upon R square. This is your K here. Potential E is equal to minus of dV upon dx. So dV is equal to E dx. So V is equal to integration of that. Simplify this, you will get potential V is equal to 1 upon 4 pi epsilon naught Q upon this R. So potential due to charge Q at any point at a distance of R, that will be KQ upon R. Intensity, it will be KQ upon R square. This is for the point charges. Now let us use this relation and simplify this question. So here when we have considered these points, origin 1, 2, 8 and so on, 1, 2, 4 and then 8 and so on. So potential due to this charge, so here separation is how much? 1. So Q upon R means Q upon 1. Due to this charge, Q upon 2. Due to the next charge, Q upon 4, Q upon 8. Now these distances are taken so that they are in geometric progression. 1 into 2, 2 into 2, 4 into 2, 8. It means the sequence is in geometric progression, that is the distance which is given here. So that you can represent 1, 2, 4, 8, 16 and so on. This goes up to what? Infinity, because infinite number of charges are there. Infinite number of charges are there placed like this. So this sequence or this series, it will go up to infinity. Now simplifying, we are getting this relation, because Q you can take common, so it is KQ 1 plus 1 by 2, 1 by 4. This is in geometric progression. This geometric progression having how many terms? Infinite number of terms. Use the relation for the geometric progression and the sum of the series up to infinity. You will be able to calculate this. So just putting all these values, we are getting K into twice of Q. Intensity at x equal to 0, it will be how much? Q upon 1 square, means kq upon 1 square, again kq upon 2 square, kq upon 4 square, and so on. So you will get kq upon 1 square, 2 square, 4 square, 8 square, and so on. Again, this up to infinite number of terms because there are infinite number of charges. Again, simplifying. So q upon 1, 2 square means 4, 4 square means 16, 64, and so on. Now again, this is in geometric progression that you can see 1 into 4, 4, 4 into 4, 16, 16 into 4, 64, and so on. So again, we can use the relation for geometric progression and we can simplify this. So again, simplifying, you will be able to calculate this. Now there is another part of this also. So what will be the potential and electric field at the above set of consecutive charges have opposite sign. So from there we can calculate all this because there are infinite number of charges. Charges are placed at a distance. Those distance maintain some sequence, and using the concept of geometric progression we could simplify this. Now you can see this example. So in this example, it is required to hold equal charges Q in equilibrium at the corners of the square. So there is suppose a square, and we have to keep these charges in equilibrium at the corners of a square. Prove that the point charge which will do this if placed at the center of the square is this. So now these charges are to be placed at the corners of the square. Condition is that they should maintain equilibrium, meaning they should be at rest. Okay. Now we have to prove that the point charge which should be kept, or which will do this if placed at the center. And we should place a charge at the center of this much of magnitude, this nature, such that all these charges remains in equilibrium. You can take this question in other way also, that what should be the value of the charge which should be placed at the center of the square so that these four charges remains in equilibrium. So we have to calculate that magnitude as well as we have to calculate nature of the charge which will be placed here. So either way we can analyze and we can proceed further. So here this is your square A, B, C, D. Charges placed are Q, 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 and Q. Suppose some charge capital Q is placed at the center of this. This is your R, this is R, this is R, and this is R. Side it is given as A. Once the side of the square is known to us, we can always calculate this small r from the concept of the diagonal side and all that. Okay. So A square is equal to R square plus R square, and from there we get R is equal to A upon square root 2. That you can easily calculate or understand. Now force on B due to Q at A. Force on B due to Q at A. So if this is positive, so obviously force of repulsion, it will be in this direction. Similarly, force at B due to Q at C. So again this will be in this direction, because again there will be force of repulsion, here also force of repulsion due to this. So it will be in this direction. So all are similar in nature. So obviously there will be force or repulsion due to this, as well as due to this. So that we can calculate force on B due to A, force on B due to Q at C, and force on B due to Q at D. So that we can calculate it. That will be how much? K Q1 Q2 upon distance square. So for this distance is A, for this distance is twice of R and R, so twice of R. Is this clear? So all those things you can represent, and we can calculate and we can substitute it here. Now force on B due to Q at O. Now see this. This is the central point where we need to consider this Q. So if this charge, this charge, this charge, or this charge remains in equilibrium, it means each and every charge in equilibrium. So this is in equilibrium, and we should place a charge Q here in such a manner that resultant of all these forces, this force, this force, this force, should be balanced, because these are the three forces experienced by this charge due to this, this, as well as this. Now there should be a force charge here, somewhere here, so that it can balance the force acting on this charge Q due to these three charges, this, as well as this. Then only it will remain in equilibrium. The same thing holds true for this. If you analyze this, then again you can consider the same thing. Due to this, it will be in this direction. Due to this, it will be in this direction. Due to this, it will be in this direction. And again, due to this, it should be in such a manner that it should balance resultant of all these forces. That is the only concept. We will use it, and we will be able to calculate whatever is required. So force on B due to Q at O. So we are getting this relation due to Q at O. Q into small q divided by distance square. So it is R square. So it is R square. Now that R can be replaced using this relation. So we have this one. Okay. Now let us find the resultant of these three forces, this force, and this force. That resultant of the forces has to be balanced by this force. Then only this charge will remain at equilibrium. So let us solve this. So total force along x-axis on that particular charge, that will be how much? F1 plus F3 cos 45 degree plus F4 cos 45 degree, because once it is squared here, and here forces are this side, and this side. This angle is 90, they are equally placed, so it will be 45 degree. Component of this cos 45 this side and sin 45 this side. So we have this x component. Okay, so this is along x-axis. So kq square upon a square plus kq square upon twice of a square plus q plus 4q, that is equal to 0. So simplifying, we have this relation. Now forces acting on this along y-axis. So it should be equal to how much? 0 if q is equal to this. It means the meaning here is summation of all forces along x-axis, it should be 0. Forces along this axis, it should be 0. Then only summation of all force. Then only this charge will be able to maintain equilibrium, because here we have this unknown charge q that will act in this direction. It will have its x component as well as y component. Y component of all these three forces have to be balanced by y component of this, and x component of all these three forces should be balanced by the x component of this. Equating all that, we can calculate whatever is desired. So we have x component, y component, summation of all the forces acting on that, it should be 0. Equating that, we can calculate that this q is equal to q by 4. Now minus sign. Minus sign means what? This side you are getting this side and this side. So resultant of this and this, it will be somewhere along this. So it means this charge should pull it in this direction, in the opposite direction. So here, if suppose these charges were positive, then this will have to negative, then there will be only force of attraction. There will be force of attraction, because due to this it is force of repulsion, due to this it is force of repulsion, due to this it is force of repulsion. If we take the component of this along this as well as this, so all these forces are either acting this side or acting this side. Force due to this should act in this direction, then it will have one component this side and another component this side. This component will be able to balance component along this component will be able to balance component along this. Summation of all the forces, these three forces as well as this force, along x-axis it should be 0, along y-axis it should be 0. Equate it, you will be able to get the value of this unknown charge as well as sign. Sign, we could calculate that it should be in this direction, so it should attract these charges Here all forces are force of repulsion. Because of this, it should be force of attraction. Then only those forces can be balanced. Once you calculate, so from there we get that it should be minus in nature, and this gives you the magnitude of the charge, that is small q by 4, 1 plus 2 root 2. So we can calculate it. So here the concept that we are using, summation of all forces acting along x-axis is 0, and summation of all forces along y-axis, it should be 0. It will have a component along this and this. So this is summation along x-axis, this will be your summation along y-axis, equate them to 0, and we can calculate the unknown quantity. So we will continue more questions in the next lecture. Thank you.